Here we are in the first lesson of unit or chapter 5 on relations. Fancy name, don't worry about it. Fancy word, don't worry about it. We're going to start off with what we call the Cartesian coordinate system, which is basically the graphing grid that you are. Okay, technology problem. All right, it's this grid. You know, the XY coordinate system. That's what we call the Cartesian plane, from a guy named Rene Descartes. 400 years ago. Sorry. What's important for you to know from this is that the horizontal line is called the x-axis, and the vertical line is called the y-axis, and the center part here is called the origin. We usually label that with an O, and then you count off starting from the origin, so it goes +5 off to the right, it's counting positive numbers to the right on the x-axis and up on the y-axis. And if you go to the left on the x-axis, you have negative numbers, and if you go down on the y-axis, you have negative numbers. Okay. And then, so here's one little trick to remember which is the x and which is the y. A friend of mine who teaches grade 6 came up with this. There's your y-axis. There's your x-axis. There you go. Never forget that again. Thank you, Rosalind. And then we identify the location of something in what we call a coordinate pair, or coordinates, or an ordered pair. I'll just highlight in there for you. And an ordered pair, hint, hint, the order matters. It's always x and then y. And you have to put the brackets around it. The brackets matter, because that is how you say to the world, this is an ordered pair, and this is coordinates on the Cartesian plane. So just get rid of this extra yellow here. And we're going to, oh, and also they're numbered. Each quarter of this is called a quadrant, and they're numbered starting with this one. We start in this one because this is where the real world happens. It's positive and positive. So it's like positive time with how far did you travel, that sort of thing. So a lot of real world stuff exists only in this coordinate, or this quadrant. So that's quadrant 1. And then for other reasons, we go counterclockwise, but there's quadrant 2 and quadrant 3 and quadrant 4. And we do normally label these with Roman numerals. Okay. Let's do example A. Let's write the coordinates of each point. So point A is right here. So we start at the origin and we count the x's first, and you're counting not lines but gaps, like how many jumps. So I'm going to go, it's 1, 2, 1, 2. So that's going to be my x coordinate. And then my y coordinate is 1, 2, 3, 4. Okay. B is over here. So I'm going to count -1, 2, 3. So it's -3 on the x-axis and 0 on the y-axis, because we're actually not moving in any amount in the y direction. Okay, pause the video, do the rest, and check your answers. So we have 6 and 3. We have 0 and -3, and we have 0 and 0. So this one is important. From the origin, you're not moving at all. You're not moving anything in the x or anything in the y, so its coordinates are just 0, 0. Write the coordinates of the point in the second quadrant. Well, that would be this, so that's point E. And point E is at -2 and 3. So we start at the origin, we go back 2, that's -2 and up 3. The coordinates of the point in quadrant 3, that's point F. And that is at -4, -3. Okay, so the plus and minus matters and the order matters. And then we're just going to complete this table using positives and negatives. So quadrant 1, like I mentioned, everything's positive because that's mostly your real world stuff. When we go to quadrant 2, our x values are negative and our y's are positive. Quadrant 3, everything's negative. And in quadrant 4, down here, our x's are positive, but our y's are negative. Oops, positive and, oops, I knew I was going to do that. Undo, positive and negative. Okay, next page. This lesson should all be reviewed. We did all this in grade 9, but we'll just go over it quickly to refresh your brains. So 3 toothpicks are used to form a triangle. A second triangle is formed by adding more toothpicks, and then we add more to add another triangle, and so on. So we're going to draw the next 2 diagrams in the pattern. So I'm going to draw what we have already, okay? And then I'm going to take a different color and draw what we're going to add. So we're going to add that and that. Okay, so now we've got an extra triangle. And then for my next one, I'm going to come back and draw again what we're starting with, which is now that. And then we're going to add 2 more toothpicks to add another triangle. Okay. So we're going to complete this table by relating the number of toothpicks, P for picks, with the number of triangles, T for triangles. So in figure 1, if we have 1 triangle, we have 3 toothpicks. If we have 2 triangles, we have 1, 2, 3, 4, 5 toothpicks. When there are 3 triangles, we have 1, 2, 3, 4, 5, 6, 7 toothpicks. And that makes sense because you're adding 2 each time. And then for 4 triangles, you've got 1, 2, 3, 4, 5, 6, 7, 8, 9. And then for 5, if you count it, we have 11. All right, now we're going to graph this. So we'll talk a couple of times about dependent and independent variables, but I'll just, for this example here, the number of toothpicks depends on the number of triangles. So you make the triangles and then you count the toothpicks. Sometimes it's really very clear. We've got an example coming up where it's very clear which is the dependent and which is the independent variable. Sometimes it's not as clear, but you can tell from the chart, almost always the top one is going to be the independent. And that's going to be your x-axis. Now, it might be labeled different. Like here it's labeled T, but that's when we talk about the x-axis, we're always talking about the horizontal axis, and the y-axis is the vertical axis. Okay, so when a table's like this, the x one or the independent one, the horizontal axis comes first. And then the one that's left over is the other one. Okay, brilliant words. Okay, I'm just going to go, since this has to go to 5, I'm just going to make each one of these one number going up by 1. And this, I'm just going to do the same thing, go up by 1. So 1, 2. But you don't have to label every one. The jump has to be consistent, but you don't have to label every single line. If it's cluttered, labeling every second one is just fine. Okay, so we've got a point. I'm going to do this in red so it shows up better. We've got a point at 1, 3. We've got 1 at 2, 5. We've got 3, 7. We've got 4, 9. And we've got 5, 11. Okay, there's all our points. Okay, does it make sense to join these together in a line? Well, it doesn't, because if you remember, a line is just a series of points that are so close together. This is the best way I know to think about a line. It's a series of points that are so close together that it looks like a line. As in, every value between any 2 points in there is valid. It doesn't work this way because you can't have 1.13 triangles, right? So the way I'm going to write that is that the points between are not valid. Try and write legibly. They are not valid. Example, can't have 1.5 triangles. Right? You can't have half a triangle. That doesn't exist. It's not a thing. Describe in words the relationship between the number of toothpicks and the number of triangles. Well, the number of toothpicks, oops, wrong pen. Number of toothpicks is, let's see, we've got 1 triangle. It's 1 more than 2 times the number of triangles. And if you're not sure where I pulled that from. Don't worry about it right now. We're going to get that. There's a process I'm going to show you to do this. Just not going to do that right now. Okay. And then write an equation that can be used to determine the number of toothpicks if we know the number of triangles. So toothpicks is going to be 2 times the number of triangles plus 1. So that's like 1 more than 2 times the number of triangles. And then let's use this equation to find the number of toothpicks if there are 27 triangles. So when you have a formula like this, it's really helpful. When you get into physics, your physics teacher will make you do this. Every physics teacher I've ever known insists that you do this. I don't know why we don't do that in math because it's really helpful. My 2 variables are P and T. And which of those do I know? Well, I know I've got 27 triangles. And it's asking me to find P, so I'm going to put my question mark there. And then when I write out my equation, P equals 2T plus 1, well, I don't have a value for P, that's what I'm looking for, and I can replace my T with 27. So I get P equals, that's 55. And then my answer is going to be 55 triangles. Because this is a word problem, and, oops, sorry, that should be toothpicks, not triangles. Toothpicks. This is a word problem, so this does require a word answer. I don't need a sentence answer, though. I just need, a number and a word or 2 words or whatever makes sense. That's okay. Okay. All right. Part H. Use the equation to determine the number of triangles if there are 83 toothpicks. Well, again, I'm going to write my P equals and my T equals and fill in what I know. So I know that there are 83 toothpicks. That's my P. So that's 83 goes here. And the T is what I'm looking for. And then I write my equation out again. P equals 2T plus 1. And then this time, because I know the P, I replace the P with the value I have for it. And then write everything else out once. So now I have an equation to solve, and I use my amazing algebra skills to solve for t. So I have 82 equals 2t, and then I divide by 2, and I divide by 2, and I get t equals 41. So my answer is 41 triangles. Okay, there you go. Next page. You're welcome to take a break right now because this is long. Students in a physics classroom determine the resistance of an electrical circuit by measuring the voltage when a current is passed through the circuit. So since we are passing the current through the circuit, this is our independent variable. And then we are measuring what happens. So this is our dependent variable, okay? And then that matches our table because we've got the independent on top. So this is going to be our horizontal or x-axis, and this is our y vertical axis. We're going to graph it. So I'm not going to go into graphing it, how to calculate it so much, but when you're graphing, you need to take up at least half the grid that you're given, because if you're taking less than half, you could double the size of everything you're doing on the graph. You want to fill up most of it, but you don't have to fill up all of it. You are allowed to use some discretion when like it makes the counting easier. So this goes up to 50-ish and our data goes up to 48. So I'm just going to make like this is going to be 10 and this is going to be 20 and this is 30 and this is 40 and this is 50. Now I'll tell you, the first time I did this, I went, oh, well, I'll go like 12 and 24 and 36 and 48. I don't know why I did that, but that was the first thing that occurred to me because these were all like 6 and 12s. But it actually made it harder because I couldn't, like, I was having to do halves and stuff. And since I could do 50, that made more sense. So that's what I did. Along the bottom, I've decided to just go from 0 and make each of these heavy lines a 1, 2, 3, 4. I still have to do some half things, but it just didn't seem worth it to, you could actually go and make this 4. Could you? No, you couldn't, because then that would be, you'd have quarters and stuff. Anyway, what I'm trying to say is, like, I've taken up, 3/4 of the 4/5 actually of the bottom axis, and I'm gone, that's fine. I don't have to go all the way out to the end if it makes each one of these something silly to measure or to count or whatever you want to call it. Okay, this is my voltage. This is my current, which is we called I. And we're going to graph the data. So I've got, okay, I'm just going to go off my paper for this. So when my current is 0.5, so that's going to be right here, my voltage is 6. So since this is 10, every line is 2, so 2, 4, 6. Okay, so there's my 1 point. And then when the current is 1.5, I'm going to go up to 18, so that's 20 minus down 2, it's right there. And at 3, it's 36, so that's there. And at 4, it's 48, which is right there. Okay, does it make sense to join the points together with a straight line? Well, definitely they're in a straight line. And yes, we can join this together because the points in between the points that we've graphed are valid. Okay, so the points between are valid. For example, we could test 1.14 amps, right? We could do that, and then we could put where it's going to be on the grid, and that would make sense. Whereas we couldn't do 1.14 triangles, so we couldn't join that. So I'm going to join mine. You're going to use a ruler. Now, while I do this, I just want to mention that when you are graphing things, accuracy matters, neatness absolutely counts, and I will hold you accountable for that. Okay, I will show you some tricks that help you do a better line when you're doing this, but you have to use a ruler, and I expect it to be neat. All right, because the purpose of a graph is for somebody to read information off of it. One thing I'm just going to mention is you're not going through your dot, you're going through the intersection of these are all called lattice lines. You're going through an intersection of the lattice line because your dot can be off center, it can be really big and blobby, or so you're aiming for the intersection of those lattice points. All right, next it says use the graph to determine the voltage for a current of 2.5 amps. So I'm going to find my 2.5 amps, and that's right here. Well, it's in the middle, right? So I'm looking at this, and rather than trying to find where the ruler is going to go and then go up and see it, I'm going to go, like, it's in the middle of this one. I know that it's in the middle because that's halfway. So and then I'm going to go up here. It's going to be in the middle between these two lines. So it's going to hit right about there. Oops. Oh, there's my little dot there. It's going to hit right about there. Not actually going to hit right on the line. And then I'm going to draw my line over here. I'm going to sort of draw these, but find the point before you actually draw the line, okay? Because you can follow it with your eye sometimes better than you can with your ruler. Like, this is terrible because it's really hard to do on here. Anyway, so I'm going to say that that's what, 29.5. Yeah, it's not. Yeah, 29.5 volts. Because it's not quite 30, but it's more than 29, because 29 would be like halfway in here. Like 29 would be here. It's a little bit higher than that. You're not usually going to get a perfect answer off of your graph. That's just the truth. Sometimes you can, like in this example here. It says write an equation expressing V in terms of I. That means that I'm going to say V equals do something to I. So I have to figure out what that is, and we're going to get into better strategies for this soon. But for now, I'm just going to say that when I equals 1, like here, my voltage right there is right on the line. My voltage equals 12. And when I equals 2, my voltage, again, it's right at the intersection, and my voltage equals 24. So I can see that my voltage is 12 times my I, or my current. So voltage equals 12 times I. There's my, my equation. And then use the equation to determine the voltage when current is 6.2 amps. So again, I've got my V equals and my current equals, and I've got 6.2 for my current, and V is what I'm looking for. So V equals 12I, so that's 12 times 6.2, and my calculator tells me that is 74.4 volts. Okay, can I check that on the graph? No, I can't this time because my voltage doesn't go up that high, my current doesn't go up that high. I'd be out here somewhere. But that's okay. Can't do it, can't do it. And then resistance, which is used an R as the variable and it's measured in ohms, is calculated from the equation V equals IR. And so what is the resistance? Well, since V equals IR and we have V equals 12I, which we can rewrite as V equals I times 12, we get that R equals 12. Okay, on 12 ohms, because again, word problems. Okay, one more little bit, and this is really important, is about discrete and continuous variables. When we were looking at the measuring the current and the voltage, these are continuous variables because they can be any value in there, any value between 0 and 4 and higher. We can measure those, so those are called continuous variables. Where's my highlighter? In the other one, when we were talking about the number of triangles, those are what we call discrete variables. Those are essentially things that you can count, okay? And so here's just some examples. Oh, and sorry, and the important thing is that when you have discrete variables, you don't connect them. And when you graph continuous variables, you would connect them, all right? So the time taken to complete a 100-meter sprint, that's going to be continuous because it, time is always continuous. And the height of students, that's also continuous because they don't, they're not like 5'6" one day and then a minute later they're 5'7". That doesn't happen, right? You're just growing a little bit all the time. Number of students who pass Math 10, that is a discrete number because you're not going to have, 17.312 students pass the course. And the same thing with shoe size, that's a discrete. Basically, these are countable things. If you can count them, it's discrete. Okay? All right, there is your first lesson. I'm sorry that was so long. There's no way I could have made it shorter. Bye.